I think technology, if you look over history, has really contributed to energy efficiency. So you talked about energy efficiency in tires, and we had some discussions down here about energy efficiency. But synthetic lubricants that are made are another component that can contribute to energy efficiency. And we at ExxonMobil have developed some new synthetic lubricants that are very interesting in their properties. And it's very much what you said. It's a combination of things that have been done in the past in different businesses and bringing those together. So in this particular example, Metallocene Catalysts are one of the catalysts that have been around for a fairly long period of time. We did some work in the 90s around polyethylene and pioneering Metallocene Catalysts, and we also have a synthetic lubricants business. And synthetics have been around for a very long period of time. Actually, synthetics were first invented in the 1930s and 40s by a company in Germany, IG Farben, who some of you may have heard of. And that industry has continued to grow over time, and it's been evolutionary. It's been little changes and then some big changes as we've kind of gone through that. But I think when you put these two together, you develop some different molecules that can help us meet the energy demands that we have out there. And for example, on Metallocene PAO, the SpectraSyn Elite product that we've developed, its properties are such that it has a very, very broad range of operating window, much broader than any other synthetic lubricant that we have. And that allows the lubricant formulators to do things that improve the efficiency both in low temperature properties of the lubricants. And when you first start up, for example, any kind of machinery, an automobile, and also the high temperature properties, it's a very optimized system, and that contributes to fuel efficiency. So we've looked at synthetic lubricants around fuel efficiency, and if you just took the US automobile fleet, which is 200 plus million cars out there, and only a third of the automobile fleet was converted from a conventional lubricant over to a synthetic lubricant, you could save about 2% or gain 2% fuel efficiency in doing that. And that 2% fuel efficiency results in consumption of just under 1 billion gallons of gasoline, a savings of just under 1 billion gallons of gasoline. It's like taking 1.5 million cars off the road. And living in Houston, I would love to get 1.5 million cars off the road. But I think that's a good example of how bringing technologies together can help contribute to energy efficiency.
Mark, I'm really glad that the way you cast that by first talking about the technology itself, which really, if you could drill all the way down to the molecules and atoms if you wanted to, you're not doing that here, but then really showing what problem that is getting at. And when you scale up then to a kind of a national fleet level, and you could take the friction question and go beyond cars into all of the factories and else, you really begin to see that you're trying to get at a national issue, an international one. So this is where materials really start to potentially solve or alleviate big issues.
There's one other thing here, and it comes through the themes here of what we've just talked, and that is it's a trend of what's happening in material science, and that is the people who are using the materials are becoming more informed. And so when now it's not our engineers talking to their engineers about how you get this high performance product built, but now there's another player in the equation, and that is the consumers of the product, who aren't just waiting to see what you come up with next so they can buy the next improved model, but they're becoming a part of the conversation of we care how you made this product, we care what you've made it from, we care what happens to it at the end of its life, we care what happens with us when we interact with this product. And while that equation has always been out there because consumers have always been consuming the products and the materials that our companies make and other materials companies make, I think the digital age and all the wonderful things that the digital technology materials are providing are just increasing the speed of the time at which it takes for a consumer to become informed enough about an issue to make a buying choice and really go with that buying choice in a way that's serious. And we've seen this happening with our Triton line of products where consumers have switched from one material to another, not because there's absolutely black and white science that just says you should do that, but because there are some trends out there and there's some debates going on in the scientific world about the use of bisphenol A in food contact applications. And consumers are going, well, why would I take the chance if there's a debate among scientists on this? I'll go towards something that's safer. And we've seen them rushing away, not based upon things that scientists in any of our labs would say is a solid conclusion, but they've rushed away to other materials. And I think this trend's going to happen in the future. And some of those conclusions consumers will make, they'll make with partial information. But I think the internet's going to allow them to make it with more and more information and get to a conclusion more quickly than we have led them to those conclusions as an industry in the past, or that they've been led through the other groups that interact in this equation, the NGOs and all the other communities that are now having this discussion. So materials innovation is going to be about unleashing the creativity of all of our scientists, but it's also going to be about understanding that we really do serve people at the end of the day who care about the products that they're going to make, and they want those products to be good quality, and they want those products to be safe so that they don't have to worry about their tire slipping off the road, or about their engine failing, or the other things that are there, or about what's happening if I'm using plastic in my life and it's the food I'm consuming is consumed in plastic. And I think the community of innovation that's out there in the material science space has gotten ourselves a lot more connected to consumers, and I think it's a good thing as we move ahead for moving material science to the next place.
Okay, there's a follow-up for two of the comments here, but I just want to make sure that I give Ryan an opportunity as well. First,
what I'd like to do is share Tom's enthusiasm about materials in a very short story. I'm a trained material scientist actually, as an undergraduate. I chose to enter a ceramics program, which was a big deal at the time. And I remember, and I was interested in ceramics because of nose cones on spacecraft and all kinds of, fabulous stuff, right? And I remember the first day of my first classroom laboratory, and the professor had coffee cups lined up on the lab bench. And I thought, oh boy, my worst nightmare. I knew it was going to be about, teapots and stuff, and I really want to do nose cones, right? So he picked up one of these coffee cups, and he hammered a nail into a board with the side of the cup. And they had me. Materials had me at that point, right? And I've had a number of wow experiences, like I'm sure you guys have over the years, just like that, about what you can actually accomplish with materials. It's quite remarkable. So the story I wanted to share with you a little bit, to talk about the subject of sustainability and biorenewables. I think, to echo again what we've heard from some of my colleagues here, I think we're genuinely excited about what's going on in bio-based polymers today. As a company, we go back over 60 years with bio-based chemistry, and I've told this story a couple times, but I mean, at the time, I guess it was Carruthers at DuPont was discovering nylon 6. We were working with castor oil, but we were using derivatives of that for perfumes and things like that. But it was actually the work at DuPont, and I think there was some work, as you mentioned, in Germany at the same time, where nylon 6,6 was developed here, and nylon 6 in polyamide 6 in Germany. And that triggered the idea in one of my colleagues from many years ago, in the early 40s, in fact, to look at polymerizing some of this lactam 11. And so, in fact, we've got, in 1949, I think they manufactured the first ton of this bio-based polymer. However, the interesting part of that story is that nobody has bought a pound of that product over the years because it's bio-based. They've bought it because of its high performance and the economics, right? And I think today's the same story, guys. I'm really excited about the innovation possibilities now as we look into new bio-based polymers, but I would still say people are going to buy them because they meet the performance and they meet the economics. And gee, if they're also bio-based, wonderful. And so we've done some work. If you got a chance to visit our table upstairs, you saw some of the work we've been doing in developing additives for polylactic acid. It's a wonderful polymer based on field corn that on its own you can't really make anything with. It runs like water out of an extruder. You can't shape it in any parts, so you have to do things to add melt strength and improve its processability and properties so you can actually hold it in your hand and do something worthwhile with it. So that was we've certainly focused on that over the last few years, and I think that we're now starting to see from NatureWorks, who's one of the largest producers of PLA, some real applications coming to light. For me, though, the next step is how you get these into durable products, because single-use products is one thing, but to try to get them into durable products is a big challenge. And if you accept what I said at the beginning, which is that people are going to buy these not because they're bio-based, but because of their performance, then to move into durables, again, you have to have the performance. And so some of the work we've been doing in our plexiglass division, in fact, is to look at engineered alloys of plexiglass, PMMA, as Ivan shared with us earlier, with PLA and other bio-based polymers. And we're finding that we're able to develop an entirely new family of polymer that is greater than 25% biorenewable carbon. And these are going to perform, and they're going to have reasonable economics. So again, these are just a couple examples, but I think that all of us are excited about the doors that have been opened for new innovations in this space.
Okay, just one follow-up on something that you said, Chris, which I think gets at one of the challenges of innovation in materials, and that's that you're often trying to optimize seemingly opposite properties. Because you mentioned with the tire material that you want to improve rolling resistance, which actually means make it less, I presume, and yet increase wet grip so it's safer in wet weather, right? So those seem to be pulling in opposite directions. And would you agree, and maybe you have some examples of how, I mean, an image that comes to mind in making materials for me as an outsider is almost like one of those circus performers that's trying to keep up 6 plates on the ends of poles, right? And you're sort of getting one over here, and it's staying up. You have 4 or 5 of them going, and this one's going down, and how do you do that? So I don't know if you can riff off of that metaphor a little bit with your own experience before we move on. And keep your answers short, because I want to stay on track. We have a second of 3 questions to get to very, very quickly. Anybody?
Well, I mean, Ivan, I think there's always this challenge in science and material science and chemistry of trade-offs. And if you can find, and we call it in our solution SBR rubber, we call it kind of the golden triangle, because our scientists have been able to find a way to, in fact, improve rolling resistance, which means better gas mileage, less friction, without compromising the normal characteristics that would generally be compromised in improving rolling resistance, which are wear and wet grip. And if you can do that, it doesn't matter whether it's a tire or anything else. If you can solve a problem without the trade-offs that generally go with the improvement in one direction and a degradation in another, and it lines up with a market need, in this case, energy efficiency, those tend to be the kind of innovations that rapidly take over an industry. And that's what's happening in these high-performance tires. And that's why when you go to a tire store today, you'll see displays where they'll tell you about gas mileage and things of that nature. But think about it from sustainability point of view. If the world were to move to these tires in any significant way, just the developed world, the estimates are by 2020, on an annual basis, we could save 100 million tons a year of greenhouse gas because of better fuel economy. So these innovations that don't sacrifice trade-offs, number one, take hold in the market very quickly, and they often have kind of far-reaching large effects. So it's not easy, it's very hard. You have to have very creative people in the organization, scientists, that can find ways to break through these trade-offs and create, in this case, rolling resistance without sacrificing other properties. Very hard to do, but important if you can do it.
One more input on this particular, and then we'll move on.
I'll just illustrate with a very quick example, because it's one of the very few things I know of that got published in the Science magazine and commercialized in the same calendar year. And that's a high-temperature elastomer. So for 70 years, you'd get elastomeric or soft polymer properties when it was low density. And if you go to higher density, like bakelites, you'd get higher temperature polymer, but it would be brittle. So we took, can you have a high temperature elastomer at low economic cost that the world can afford and at the same time make it in existing infrastructure. So the key discovery there in materials was 2 different catalysts in the same pot and have that polymer chain transfer between those two. So that led to very fast innovation, but of properties that have been known, studied, and documented for 70 years. You absolutely cannot win on both axes. But it is possible, and the new technologies and new material science allows us to do that, which was never possible before.
Could I just add one
Please,
quick thing
yeah.
on that? The other great example of that is our block copolymers, where now by working at the nanostructural level, we can actually build conflicting properties into different parts of that molecule. So that's another way we can address this very conflict you're talking about.
So I guess you would all admit that you're kind of like the rest of us. You want to have your cake and you want to eat it too, right? So let me segue then into the next question, which is really about cultures of innovation. Because it takes a lot of science, takes a lot of engineering, a lot of good management, and a lot of other things to nurture a good idea, an idea in the materials realm, so that it actually becomes a consequential new material that people can afford and really put to use. I've always been interested in cultures of innovation, actually institutional cultures. I've worked in many places, probably too many. Each one has its own peculiar culture. And I'm sure that's true of all of the places where you work. So I'm wondering if you can talk about how your companies try to really nurture that and perhaps ferret out things that inhibit innovation. And who's going to raise their hand first?
I'll start.
There you go.
So I think one of the things you didn't mention was commitment. And it takes a lot of commitment to develop technologies and innovation. And we at ExxonMobil are committed to technology and innovation to meet the world's energy demands in a sustainable way. It's a very important principle for our company as we kind of go forward and we develop technologies. I think when you look at commitment and developing things, and you look at our company, we have a large number of scientists and engineers that work in our company. We have about 18,000 that work on innovation inside the company. We spend over $1 billion a year on research and development across the company, and all these things help develop some of the products that we talked about a little bit here tonight. And when you talk about that commitment, it also takes collaboration. And we work closely together with each other, and then we also work with people on the outside and universities on the outside. So I'll use an example of our global climate and energy project that's run out of Stanford University. We were a funder there. We spent $100 million over 10 years. And that whole project is geared at meeting the world's energy demands in a sustainable way as we go forward. And that's a very, very important aspect of it. But what I really like about what I see in our engineers and scientists is that perseverance. It's so exciting to see them work and work and work. And I assure you, we do a lot of experiments, and not every one of them goes exactly the way you would like it to go to get the result that you're looking for. But when you have that breakthrough and they come running down the hall, they are so excited about the new product. I mean, we talked about being excited about materials, and when we developed Metallocene PAO, that was a big breakthrough for us. So I think those are the things in my mind that really help foster that innovation and technology development.
Following on that just for a moment, I imagine the situation is somewhat similar as in a pharmaceutical context where for every successful product, something that actually makes it from an idea out into the world, that there are 100, 1,000, 10,000 failures. I don't know if this is true, but
We don't like to call them failures. We like to call them learning opportunities.
that's what I meant to say. Learning opportunities.
Because you always learn from everything that you do when you're doing experiments, and it helps guide you with where you want to go next and what are the things that you need to do.
Right. And that adds to your knowledge base. And,
Yes, yeah,
and you
absolutely.
might, from one of those learning moments, you might actually have the breakthrough
Yeah.
in another area. Anybody else on cultures of innovation in your company? I'm going to go to Ryan first.
So I consider myself privileged to work in an R&D organization for a lot of the reasons we just heard from Mark. I don't know any of the folks in my R&D organization that aren't excited about trying to work on things that have societal impact. They come to work every day thinking they can do something that's going to make people's lives better. I remember coming out of graduate school, and I came out at a very good time, so there were a lot of job opportunities for me. And if I think about the one I selected something that would give me an opportunity to develop, at that time it was chemical vapor deposition coatings for improving the efficiency of everybody's windows in everybody's house. And you all use them today, by the way. And I took the job because of that, because it could make a difference. And I think my organization's the same way. I find that, the entire organization, but particularly the last bunch that we've been hiring over the last few years have been really insistent about trying to come in and work on something that'll improve society somehow.
So some hands over here.
Well, I'd certainly agree with Ryan's comments, and I think that motivation is really central and really resonates with our own research and technology organizations. As I think about this, as you create that atmosphere, you can work on structures, putting together the right multifunctional teams, get the right team structure in place. We can work on our processes. How do we generate ideas? How do we select the best ones? What's our stage-gated approach to pursuing programs? Those things are important. But then there's the behavior, the cultural aspect, which is really the most important part of this. I like to say that good culture and behavior will overcome bad structure and process, and bad behavior will defeat the best structure and process. So if you work on one thing, you got to work on the culture. And culture is created by leaders. Pick the right leaders to create the culture that you want around innovation. I look for leaders who bring together market insight and foresight with technology insight and foresight. That's where the opportunities are created, between the technology and the market. Where's the market today? Where's the market headed? What technology do we have today? What technology do we think we can develop? People who bring together market insight and foresight with technology insight and foresight make good leaders for this. Secondly, they need a tolerance for uncertainty. You cannot eliminate uncertainty. You have to live with it, reduce it over time. But people who are too quick to make the decision, who can't tolerate that uncertainty, really are not really cut out for this sort of thing. And part of that is having a value for optionality. I'm not sure this is going to work, but if it were to work, then and if this happened, then we'd have something. And if you can't really see those scenarios and understand the value of optionality, it's not going to work. And I'll add just one more characteristic. There's got to be a certain ruthlessness about these leaders too, right? They've got to be able to make the tough calls. They can't have pet projects. They have to have a certain dispassionate approach to the innovations they're driving in order to be successful. So those are, for me, the key elements of creating that culture.
But when you say ruthlessness, I mean, do you mean that there's some criteria, some metrics at which, what kind of decision? We're stopping this project, or we're going to put everything into it?
We've already heard it, most things that we work on are going to fail. So if you like to be right, say no to them all. That maximizes your chances of being right. But we know that value can be created by that approach, but it can't be created if you pursue too many things for too long.
Sister, you wanted to weigh in?
Yeah, so second what Mark said about commitment, and one piece of data you might be interested, if you add up the R&D budget for the 6 of these companies represent here, it's more than top 100 universities spending on their entire chemical engineering and chemistry departments. So that commitment is absolutely vital. Yet, we all feel privileged to do R&D. It's not a right in industry to do R&D. We invest those dollars so it makes life better for all of us that they're also willing to pay for. And this is where Tom was saying the intersection between marketing and R&D is so critical. We know in materials industry, if you go back 70, 80 years, it takes on an average 17 to 15 years to take products to scale. And referring to your book, Ivan, scale-up is something that is ignored in general, but that sometimes makes the difference between a possibility versus practicality of a product. The society doesn't benefit if there is no product out there, right? So we absolutely need to be committed. We also need to make the decisions, but it also takes that passionate scientist, material scientist, or multidisciplinary scientific group that will just say it is possible to do something, and yes, I'm going to do it in an economical manner. But I do not know if I'm going to succeed in 3 years or 5 years, and we need to nurture that. If we don't nurture that, we might as well not start it.